Beams are long straight structures designed to undergo transverse loading. Designing beams requires a good understanding of the variation in the internal shear force and bending moments at each point in the beam. These internal forces are key to identifying potential points of failure in the beam as they directly influence the stress and strain. Shear force and bending moment has a wide range of applications. For example, these shelving arms in the image on the left must be designed to resist the internal loading in the arms caused by the lumber. So, what is shear force and bending moment? Shear force is an internal force transferred along the length of the beam as a result of external forces and support reactions. Similarly, bending moment refers to the internal moment due to these external forces and the support reactions that cause the beam to bend. These act over the cross-section of the beam and can be exposed by hypothetically cutting the beam. Since shear force and bending moment varies with changes in loading, shear force and bending moment functions, Vx and Mx, are used to express the internal forces over the length of the beam. Discontinuities in these functions are typically found at points where there is a change in loading, hence Vx and Mx are typically represented in a piecewise manner or by using singularities. A method to solve for shear force and bending moment is to section the beam to form a piecewise function. We define the origin as the leftmost point of our beam, then cut x distance from it. We cut the beam between points where there is a change in loading, then we use the section to obtain shear force and bending moment functions by using the equations of static equilibrium. We then repeat this process until we hit the other end of the beam. Let's use an example to show how we go about this process. Here we are given a beam which is subjected to a distributed load between points B and D. We start by defining the origin at the leftmost point of our beam, point A, and then solve for the reaction force at point A. We do this by taking the moment at D, and we find that the reaction at A is equal to 1/4 omega naught A. Next, we start sectioning. We first cut the beam between points A and B to find the shear force and bending moment. This section finds the functions for when x is greater than 0 and less than A. By using the free body diagram of this section, we assume that the exposed internal shear force V is downwards. Then we write the summation of forces in the y direction and isolate for V. By doing so, we find that Vx equals 1/4 omega naught A. Next, we assume a counterclockwise bending moment M and write down the equation of the sum of the moment about the end of the section at point alpha. We then isolate for M and find that the equation for bending moment is mx equals 1/4 omega naught ax. Next, we cut the beam between points B and D. We draw a new free body diagram of this section and find the shear and bending moment functions for when x is greater than A and less than 2A in length. By applying the same process as before, we can obtain Vx and Mx for this section. Another interesting thing to note is that the function for bending moment can also be found by integrating the shear force function. Hence, we can take the integral of Vx from 0 to x for each section and obtain the equations for bending moment.
Using a piecewise function does work for representing the equations for moment and shear. However, with more applied loads and moments, the expressions will become increasingly complex as more sections will be needed to solve for the function. Hence, singularity functions are used to simplify the representation. Singularity functions work by using Macaulay brackets and express the shear or bending moments of the beams in one equation. These act to turn on and off certain parts of the equation according to the examined section. In other words, if the values in the bracket are negative, treat that part of the expression as a 0. If it's greater than or equal to 0, then replace the Macaulay brackets by parentheses. By using this, we can combine the equations for each section of the beam into one. In the previous example, we can represent shear force and bending moment functions of the beam using singularity functions. Looking at the beam, we notice that the distributed load begins at x equals a. Therefore, the discontinuity point of the function that appears in the Macaulay brackets will be at a. If we consider the section before x equals a, we notice that shear equals 1/4 omega naught a, and moment equals 1/4 omega naught ax, when x is between 0 and a, as found in the previous background section. Considering the section when x is either equal to or greater than a, we notice that the same equations found in the previous background section are still viable. Noticing that the negative omega naught times x minus a term is only included in the equation for shear force when x is greater than or equal to a, we can combine the functions and obtain the singularity function for shear force, where the discontinuity we noticed before is the condition in the Macaulay brackets that turn that term in the function on or off. If x is before a, then 0 is less than x, which is less than a, resulting in a negative value in the brackets. This value will be ignored, and the term x minus a will be evaluated to 0 instead, allowing for omega naught times x minus a to be ignored when calculating the shear force. If x is after or equal to a, then the additional distributed load should be considered in the calculation for shear force. Since x is greater than or equal to a, the value in the Macaulay brackets will be positive, and the brackets are replaced by parentheses so that the term omega naught times x minus a is considered. The same process can be done for the equation for bending moment, where the negative 1/2 omega naught times x minus a squared term is to be turned off or on depending on the value of x. This results in the singularity equation for bending moment. It is also worth noting that the equation for moment can be obtained by integrating the equation for shear as shown. These equations were obtained with an example that involved a distributed load that was open-ended to the right. If a distributed load is in the middle of the beam and doesn't extend to one end, the equations for shear force and moment can be found by using a combination of open-ended loadings. As shown in this figure, the equation for the distributed load at any point of the beam was obtained by considering the points where each load starts. As the equation for shear force can be obtained by integrating negative omega of x, v of x can be found through the following steps.
Alright, here is a shear force and bending moment example using singularity functions. For the beam and loading shown, find the equation for the shear force and bending moments at any point. So that is the example we're going to be working with. So the first thing we want to do is determine the reaction forces at A and B. And to do this, we're going to convert the distributed load into a point load, which is going to be equal to the area of this loading triangle here. So if we use the equation for the area of a triangle, 1/2 base height, we get the total load is going to be equal to 1/2 LW. And for reference, we're going to be assuming that W is a negative number since it is weighing downwards. Now, since the summation of the forces in the y direction is 0, we get this equation, that the total load plus the reaction force in the y direction at A and the same at B is equal to 0. And since the beam and loading are symmetric, we can find that the reaction force at A and B are equal to negative 1/2 the total reaction force, which is equal to W. So we take this equation, we rearrange it because these two here are equal, and we solve using this value that we got earlier to find that A and B, the reaction in the y direction, is equal to negative 1/4 LW. The next step is to simplify the problem by rewriting the original load with these two equivalent loads. The load shown above the beam is negative, so it's pushing downwards, and the load shown below the beam is positive, so it's pushing upwards in the upwards direction. So when these two loads are superimposed, the result is just the initial load. This portion cancels out with this portion, and we get this nice triangle again when they're added together. Now, we model the problem in this way because it reduces the number of Macaulay brackets that are required in the shear and bending moment equations. Because the negative load is continuous over the whole beam, so it's just one continuous line. We don't have to use a Macaulay function for it, or Macaulay brackets for it, and so we only need to use Macaulay brackets for the positive load, the portion that's down here. And if you're wondering, the negative is down here because W itself is a negative number, so these will cancel and become positive, and we're pushing upwards. So we're going to split this load into these two loads because it's going to make our lives a little bit easier later. So now we need to create the functions to represent the load on any point in the beam. And the easiest way to do this is by considering these two loads one at a time. When we're looking at just the negative component of the load, we find that it is equal to 2W over L multiplied by X. So that's our equation here. And this component of the equation is just the coefficient that represents the slope of this line here, and X is our independent variable that is representing the distance of our point from A. So we pick a point anywhere here, and X is the distance between A and that point. Now, when we're looking at the positive component of the load, we find that it is equal to negative 4W over L multiplied by X minus 1/2 L, and that's in Macaulay brackets. And this is where the Macaulay brackets are useful. When the term inside them is less than 0, the brackets evaluate to 0. And so in this case, that means the upwards load doesn't come into effect until after point C, which is exactly what we want. So since half of L is the length from A to C, X minus 1/2 L doesn't become positive until after point C. And so for any time before this will be less than 0, and so it will result in, this will just evaluate to 0, and then afterwards it will evaluate to, this will be, the components in the bracket will be positive, and so overall it'll evaluate to positive, and then we get our nice positive component right here. And then there's just one more step for finding the load function. We add this function and this function together to get the equation for the overall load, and Wx is the load, where x is our distance from point A, and here is the load expressed in W and L. Next, we want to find the function for the shear force in the beam, and we do this by integrating the load function. The only integration rule we need for this is just this one, that the derivative of ax to the n is equal to a over n times x to the n minus 1 plus our integration constant. So when we integrate this expression here and use just that integration rule, we get this expression. The last thing we need to do in this step is determine what the integration constant is going to be. And since the shear force at point A is equal to the reaction force at point A, which is whether x equals 0, we want to take the reaction force at point A as the integration constant. So if you remember from above, that is just negative 1/4 WL. And so that is our complete function for the shear force at any point x along our beam. Now, if we graph this function, we get something that looks a little bit like this. And you can see the shear force in our beam goes from what it is at point A over here to what it is at point B over there. Finally, we want to obtain a function for the bending moment in the beam. And to do this, we integrate this function again. And when we do so, using the same integration rule, we get this expression, and we have a new integration constant. Now, this expression is going to form the basis for our bending moment function in the beam. And when x is equal to 0, all these terms are going to be equal to 0. And when x is equal to 0 in the beam, that's at point A, and there's no bending moment at point A, so the whole function needs to be equal to 0. So our integration constant c also needs to be equal to 0. So when we take c as 0, we get this function for the bending moment in the beam, where m of x is equal to this. And when x is equal to 0, or we're at point A, this will all evaluate to 0, and because there's no bending moment at that point in the beam. So it all makes sense. And finally, if we graph the bending moment function, we get this graph where x is going this way and our bending moment is here, and at A, the bending moment is 0, and then again at B, our bending moment is 0, and as we can see from the shape of the graph, it is highest or lowest, but greatest in magnitude at point C, so right in the middle of our beam. And that is the end of the shear force and bending moment with singularity functions example.